Hi, we're going to talk about motion in space. This is section 13.4 of the Stewart textbook. We'll talk about motion, velocity, and acceleration, and then we'll talk about components of acceleration, so decomposing acceleration into components and circular motion. So say a particle with constant mass is moving in R3. That's the motion in space, three-dimensional space. Its position at time t is given by a vector function. Call it r of t, say, just to give that position a name. Its velocity at time t is the derivative, the vector derivative of the position. So if r of t was the position, then the derivative r prime of t is the velocity. And that's a vector function. This is the vector velocity that keeps track of the direction of motion and the speed of motion. The speed at time t is the magnitude of the velocity. And we saw speed earlier in our discussion of arc length and curvature. Finally, the acceleration at time t is how fast the velocity is changing, or the rate of change of the velocity. Or to be more precise, it's just the derivative of the velocity. Now, this is a vector function because position is a vector function, so its derivative, velocity, is a vector function. And the fact that velocity is a vector function means that its derivative, the acceleration, also is a vector function. So this is keeping track of the amount of acceleration, the rate of acceleration, as well as the direction of acceleration. Newton's second law is that the force F acting on a particle is equal to the mass times the acceleration. Famous F equals ma. Now in this case, I've made them be vectors. So this is saying that the amount of force, the size of the force, is equal to the mass times the size of the acceleration, but also the direction of the force is giving the direction of the acceleration. They're pointing in the same direction. These vectors are just scalar multiples of one another, and the scalar is the mass. We are allowing the force and the acceleration to change over time. So these are functions of time. And the equation that's written here reiterates that acceleration is the second derivative of position. We are assuming that the mass is constant. If the mass could also change over time, then you have a little bit of a different situation. But that's a story for another day. So in this example, we have a force, F, which is changing over time. It has components given by 24t and 16 minus 8t. So apparently the X force is increasing, and the Y force is decreasing or becoming more negative. And this force is acting on a 4 kilogram mass, which is sliding around in the xy plane, and we would like to find the position of the mass in 3 seconds, given that it's initially, at time t equals 0, initially located at the point 1813 with 0 initial velocity. To find this, we can start by finding the acceleration. According to Newton's second law, the acceleration is the force divided by the mass. So we take this force vector that was given and divide by the 4 kilogram mass to get an acceleration of 6t, 4 minus 2t. And then since acceleration is the derivative of velocity, that means that velocity is the antiderivative of acceleration. So I can find velocity by integrating acceleration. So to find the velocity at time t, I would integrate the acceleration from time 0 to t. And we can go ahead and solve that. So we can add the v of 0 back onto the other side. V of 0, the initial velocity was given as 0, or vector 0, 0. And the acceleration we figured out as 6t, 4 minus 2t. So that means that the antiderivative of that is 3t squared, 4t minus t squared. And that's what's going in here, just with letter u instead of t. That's going from 0 to t, and we end up with 3t squared comma 4t minus t squared. So now we know the velocity at time t. So with that velocity that we found for time t, we can now find the position. Since the velocity is the derivative of position, that means that conversely, the position is the antiderivative of velocity. So we can integrate velocity to find the position at time t. So what's written here is the fundamental theorem of calculus. The integral is subtraction of antiderivatives. So we can fix that subtraction by adding the r of 0 onto the other side and integrating the velocity. So r of 0 was given, the initial position was given to be the point 1813. That was here. It said located at 1813 at t equals 0. And then the velocity we figured out, then we can integrate that. Integral of 3t squared is u cubed. Integral of 4t is 2u squared. Integral of t squared is 1/3 u cubed. That's going from 0 to t. So when we plug in t and plug in 0 and subtract them, we get this position vector, or this position point. So by doing two integrals, we were able to find the position at time t. That's r of t for any time t. The question asked for the position at 3 seconds. So we plug in t equals 3, and we end up with the point 4522. And that is the position of the particle at 3 seconds. A question for you. A bumblebee is flying around. A bumblebee is flying around from noon, t equals 0 hours, until 2 p.m., t equals 2 hours. So it flies around for 2 hours. And its position, its location is given by r of t. And we're given that it starts in a hive, and at 2 p.m. it returns to the hive. R of 2 equals r of 0. So with those, which of the following are true? The integral from 0 to 2 of r of t is 0. The integral from 0 to 2 of r prime of t is 0. The integral from 0 to 2 of r double prime of t is 0. Or it could be more than one of the above, or it could be none of the above. Well, the answer is that, to tell you the truth, it depends a little bit on how you interpret it. I think I would say more than one of the above. So certainly the integral of r prime of t from 0 to 2 is 0, because this integral of the derivative is the antiderivative r of t from 0 to 2. That means r of 2 minus r of 0, and those are equal. So this difference is 0. And if we're being precise, then I suppose that's a 0 vector, and I guess all of these would be 0 vectors really, rather than 0 scalars. So B is definitely true. Depending how you interpret it, I think you could say that probably C is also true. This integral of the second derivative, well, the antiderivative of acceleration is velocity. So we're doing r prime of 2 minus r prime of 0. Well, then perhaps r prime of 0 and r prime of 2 are both 0. So that that would say that the bee starts and ends at rest. So if the bee starts and ends at rest, then r prime of 0 and r prime of 2 are both 0, and then we would get 0 minus 0, and that would be 0, and C would also be true. But that's an interpretation. So perhaps the bee doesn't start and end at rest. Perhaps it's moving around within the hive. So that just depends on how you interpret that question.